don't know yet, this is the energy weapons talk. There's been a few changes. So I'm going to go pretty quickly through here. We're pretty short on time, so there's going to be a chance at the end for any questions you have. If it's a good one, go ahead and interrupt me and I'll try and answer it, but keep it short. The basic idea. We've got, how to go here? Starting off with some kind of energy, probably wall current, maybe batteries, who knows what it is. You want to do something with it. You don't want to just throw a battery at whatever you're trying to attack. That's not going to do a whole lot. I mean, yeah, that's a kinetic energy weapon. Okay, I admit it. But, thank you. I'm saved. So, you have some effect in mind. Sometimes you just want to disrupt the operation of whatever you're attacking. Sometimes you want to actually permanently destroy it. Obviously, disrupting the function of something is easier than destroying it, in most cases. Sometimes it's a lot easier to destroy. But you're going to have to get your weapon, or get your energy downrange somehow. We've got a lot of different types of energy that you can use in a weapon. A lot of these you're already familiar with. Kinetic weapons, guns, knives. Let me go backwards here. I did not mean to hit that. So, you're all familiar with kinetic weapons. I'm not going to talk about them today. I don't think you need that. Chemical and thermal weapons. You're here in Las Vegas, you know about thermal weapons. Chemical, we're talking about bombs, acids, stuff like that. Who cares about that? But there's sonic weapons. There's a lot you can do just with sound waves. You can, there's current weapons in existence that, for instance, the gut buster. This is, all it does is output a nice loud sound at a low pitch, carefully tuned low pitch, admittedly, and it makes you nauseous. It's a pretty damn simple weapon, but I'm also not going to talk about that. Lasers, way too expensive. We're trying to talk about doing things cheaply here. Yeah, you can play around with lasers, but not on our budget. So that pretty much leaves us with radio weapons. You can, no matter what kind of energy you're talking about, you have to get it to your target. Either you're going to bring the weapon itself to the target and use an area effect, use an area effect kind of weapon. It's going to affect everything near the weapon. It's very wide, you don't really have much choice about what's going to get affected, and you can't deliver a whole lot of energy to a specific target unless you get really close. Directed weapons, okay, you don't have to be right on top of your target, but you can't affect a whole range of targets at the same time. We can get energy from a lot of different sources. Molecular bonds, that's slow. You all know about acid batteries. There we've got some almost molecular bonds working there. Fire, you know about that. Electric and magnetic fields is really what we're going to want to deal with here. We're talking about radio. Radio is already electromagnetic radiation. Electromagnetic fields, that's right up our alley. It's going to be a really easy thing to work with. And I'm going to spend most of the talk discussing how to manipulate those. Specifically, when we have radio waves, it's just another photon, just like light. It's a self-perpetuating field. You start with one field, an electric field, that's going to collapse and create a magnetic field. That collapses, creates the original electric field again, and that's how it propagates downrange. So you've got to make sure whatever target you're going for, you're going to be able to get these kinds of energy fields downrange. Don't try and go through metal walls. It's not going to work. Neither electric nor magnetic stuff is going to get down there. in order to do a lot of damage, once that energy gets down there, we want to have a lot of energy, generally in a short time. So whatever form we're starting with, storing our energy, we want to be able to release it quickly. That's the fast release forms I'm talking about here. Batteries are slow. So we can start off with batteries, but we're going to have to convert it into another form that we can release more quickly. So, basics about RF radiation. All photons are generated by accelerating some kind of charge. Maybe it's electron, maybe it's proton, maybe it's an ion, who knows. It's some kind of charge we're going to accelerate. We can accelerate these charges lots of different ways. It doesn't take a whole lot of creativity. There's a lot we can do with it. And we have control over this spectrum. There's a lot of details about the spectrum that I'm going to go into. So, how to accelerate? We start off with charge. It's going to flow down a wire, generally in our electric circuit. If we bend that wire, then the charges have to accelerate to go around the bend. And as that current flows around the bend, it's going to emit photons. It's probably really low frequency, but they're going to be emitted. We can control the bend, the current, and other characteristics of the circuit to control the type of energy that we're going to emit from this bend. That brings us to antennas. This basic bent wire is the most basic form of antenna you can think of. A lot of you have already seen them. They're called dipole antennas. Start with a conductor going straight and then bend it 90 degrees out. And that bend right there has a lot of effect over how you radiate energy. So it looks like a big T, this antenna. You're feeding energy up the shaft and out along the sides. And the lengths of the wires, what you make the wires out of, is going to control how well you're able to radiate energy. The biggest thing that we're going to look at with the spectrum of a radio signal is a coupling. We need to get our energy into the target. The target is going to have some kind of electrical or magnetic characteristics which will control how well it's able to pick up energy. We're radiating energy. The better we're able to match the energy that we radiate to what the target can pick up, the more energy the target will pick up. Basically, when we're coming down, we're looking at any radio weapon, it's just a big transformer. It's an air gap transformer. We got a coil somewhere generating a magnetic field. We got a coil somewhere else, which happens to be the target, and we're going to couple energy between those two. A lot of the control for how this coupling works is going to be the resonance of both the generator and the target. If you're looking at a computer, for instance, we've got a motherboard sitting in a case. That case, often, more times than not, especially in the US with the Fcc regulations, is going to be a metal case. And because it has to, it's going to have ventilation holes in it. We can get radio energy into that case, and that case, that nice big metal case, is going to resonate at some frequency. That's a cavity resonator. And generally this rectangular case is going to resonate at a lot of different frequencies because it's not... How many of you have seen a computer in a spherical case? That's really the only time it'll resonate at one frequency. If you look at a cubical case, a rectangular case, anything like that, look at the sizes of this case. The width, the height, the depth. These sizes are going to tell you what frequencies it'll resonate at. And I'm not going to get into the formulas there. It's basic high school physics. Pick up any physics textbook from high school and you can get all the formulas you want to calculate the resonance of this computer case. But these cavities which resonate for us, they're just special cases of waveguides. If I have a resonating cavity and I open both ends, I can channel energy from one end over to the other. It's guiding the wave, these radio energy along the cavity. Radar systems typically use waveguides to channel energy from whatever the generator is to your antenna. And you're used to seeing these big dish radar antennas. Well, there's a waveguide plugging into the back of that thing. And if we're careful, we can use these waveguides and cavities in order to not just generate our own energy, but direct it properly. So I'll get to that a little more when I come to some concrete examples. SNR is a signal-to-noise ratio. Now, signal-to-noise ratio, I spoke about the cavity of this computer case resonating at certain frequencies. For the purposes of our weapons, those resonant frequencies are the signal. We want to get as much of that energy over to the target as possible. Whatever we have on other frequencies is just going to be thrown away. It's wasted energy. So we'd like to be able to tune our weapons to these frequencies, but unless we know the target ahead of time, we aren't going to know its resonant frequencies ahead of time, so it's a trade-off here. Either we have a broad band of energy that we're transmitting, and we're going to waste a whole lot of it, but we'll be able to affect a lot more equipment, or we're very finely tuned, and we can only affect a few different machines. So, when I direct energy at a cavity, or even an electronic circuit, I'm driving that circuit with my energy. My energy is coming in, and it's going to try and impose an oscillation inside that cavity, or in that electric circuit. This is driven, it's driven resonance, really. Some of you have taken electronics, some of you have taken physics, and you know about the resonance of RC circuits or LC circuits under a driven source. I'm driving a signal onto that, and it's going to resonate at certain frequencies. Generally, that's different from the frequency that the circuit will resonate at if it's hit with an impulse. It's not always different, but generally it is. And this is another decision we have to make with our weapon. Are we going to continuously bombard the target with energy, or are we just going to hit it with one big pulse? Now, if we want to bombard it with a lot of energy for an extended period, we've got to be able to generate a lot of energy. And that's a really hard thing to do. Now, on the other hand, with really cheap and basically wimpy components, you can generate a large impulse very easily. So that's going to be our preferred method. And you're going to deliver however much energy you have in a very short time. That's an impulse. And you have the same energy, whether you're doing it as an impulse or spread out, but the power is a lot higher. Power is energy divided by time. So the shorter length of time I can deliver that energy, the more power is delivered. Now, a lot of circuits, when you want to disrupt them or destroy them, it's really the energy that counts. It's not the power. But you can get a lot more into the circuit by using an impulse, because generally the circuit is going to change its operation slightly when we start driving it. Let's say we have a computer. It's got these long address lines. These are wires. They have corners. They have bends. They're all antennas. If I start driving a signal at it, and I manage to couple that signal into those address lines, the computer's going to crash. It's not going to be destroyed, it's just going to crash. Now the computer's operating differently. It's no longer running Quake. It's just sitting there. It's doing nothing. And now all of a sudden, that driven signal that I was trying to couple onto the computer very well may not work anymore. So now I'm not going to couple any more energy in there. I've done nothing. On the other hand, if I hit it with a big impulse, then I couple my energy onto that wire, and before any protective devices can take effect, they all take a little time to do their job. Before they can do that, I can damage transistors, I can damage diodes, maybe I can blow some fuses. Who knows? This is going to be permanent damage. You aren't going to get around that. If I blow a fuse, sure, okay, fine. Somebody can get in there and just replace the fuse. But if I blow one of the transistors on your CPU core, you ain't coming back. So we have I need to generate some kind of signal that I want to send out. When I'm eventually going to send downrange is coming from some signal that I'm generating somehow. That's, for the purpose of this talk, the transmitter. It's generating whatever signal is eventually going to be converted into a whole bunch of photons shooting out my antenna. We can use a resonant circuit like I have on the left. This is a classic tank circuit. We have a capacitor right there, and we have an inductor over there. Really cheap Radio Shack components. You can get them for 50 cents, no problem. The capacitor is going to build up energy in an electric field. Eventually it'll collapse, sending energy over towards this inductor, which will collect that energy in a magnetic field. That'll collapse, sending the energy back over to the capacitor, which is going to create an electric field again, and that's going to just bounce back and forth. The size of this inductor and this capacitor and the parasitic resistance of this circuit will control how it resonates. I'll talk about parasitic resistance a little later. You guys saw the frame, heat bad, cold good. That's the parasitics page. So this circuit, on the other hand, I can't generate impulses with it. We've already decided impulses are a good thing. So this is useless to me. If I was a military contractor with millions of dollars to spend, I could use this to do something. But I don't. So I like spark gaps. Spark gaps are wonderful things. I have a wire here, and I have some kind of shell coming around it. That shell is not connected to the wire. If I pump charges through this wire, once I build up enough of a voltage, it'll jump across that gap right there. And that will cause the inside of this cavity to resonate. We're back to the resonating again. That energy will be able to come out the open end here. This is a spark gap transmitter. It's a wonderful thing. It's a very broadband device. I can send out energy on a whole lot of frequencies with this thing, mostly controlled by the width of this cavity, not the length of it, the width. So the wider this cavity, the lower frequency I'm going to send out. And if I use really sloppy construction on this cavity, I can send out energy on a whole lot of different frequencies. That spark will deliver whatever I want. All I have to do is send a DC current across that spark, just let it go, and as soon as that spark starts and as soon as it stops, I get a nice big pulse of photons, an impulse. So I have to have some kind of power supply. Probably batteries, probably the wall, who knows what it's going to be. It's going to give me energy that doesn't do what I want. I'm going to run that through some kind of signal generator and some kind of transmitter to generate energy in the form that I like. It's going to be an impulse if I want it to be an impulse. It's going to be a widespread burst of power if I want that. And it's going to have the frequencies that I'm interested in. Then, of course, I have to shove it out an antenna. It doesn't do much to have the energy and just sit on it. I've got to send it to my target. Antenna design is a very complex subject. It's way beyond this talk. But we can use waveguides, these resonant cavities I was talking about before. All we have to do, go back here one, That cavity there is functioning as a waveguide. The signal is going to resonate in here and come right out the end here. That's waveguide. It's channeling my energy. I'm going to have pretty much a conical beam of energy coming out of this thing. And wherever I point that, that's what's going to get the radio signal that I'm sending. So the military has a lot of money to spend. We don't really care about them. They have too much money. This right here is something Lynn Schwartau likes to tell us a lot about. This is a current multiplier. I send a current in here, and I detonate this explosive. The current is going to run through this coil. These and these are all one coil. It's a kind of cross-section here, wrapped around the whole device. This right here is a copper sleeve around the explosive. If I start the explosive burning on this end, it's going to shove that sleeve against these wires and short it out. That inductor, the inductance of this device is going to change as this copper sleeve contacts these wires. But I have the same magnetic field. It's an inductor is going to generate. Yeah. An inductor is a device that trades off magnetic energy with a current going through it. If I know the energy and I know the inductance, I can tell you what that magnetic field is. On the other hand, if all of a sudden I change the inductance, I've still got the same magnetic field, the current is going to have to change. That's how this device works. It's used as an explosive. It's a one-shot device. What do we want for it? This, on the other hand, is a nice, cheap device. You can use it as much as you want. This is a resonant cavity made from a standard old copper pipe you can get in your hardware store. I have an automotive spark plug drilled in through the end here. This is my spark gap. Same thing I was talking about before, except I went down to Cragen, spent 35 cents, got a spark plug. There's my spark gap. This spark in the cavity is going to generate energy, or I should say it's going to condition the energy that I feed to this spark plug. That's going to bounce around inside this cavity, and the size of the cavity is going to control the frequency. I have, once again, cross-section here. These are coils that I just wound myself that pick up the energy that's resonating inside the pipe. And I send it to a standard old cell phone antenna stuck on the back window of my car. If I drive this wire right here off of the ignition coil from my engine, this is going to sit here sparking. It's going to generate a bunch of pulses. If this pipe is the right size for cellular phone signals, then I have a bunch of really nasty, noisy, disgusting radio energy coming out of this antenna, and anybody trying to talk on the cell phone near me isn't going to work. Their call's going to get disconnected. They're going to have a really noisy sound at best if they're on an analog phone. If they're on a digital phone, they're just going to drop. And that scumbag who's in the fast lane, speeding up and slowing down with his cell phone pinned to his head, is suddenly going to be off the conversation. Whoop. Where did I go? And that only cost me $40. But a more interesting example is what we call the radio blast cannon. This is a much higher energy device. The purpose of this device is to make a computer release all its magic smoke. Nice little puff of smoke, maybe some sparks. Who knows? It's a spectacle. It's supposed to look nice. This is not disrupting a circuit. This is destroying a circuit. Just in case you didn't know, that cell phone jammer is an example of disrupting. This is destroy. We have a stack of batteries. How do you get batteries? Go to Costco, buy a pallet of car batteries. really cheap. You get a lot of energy storage in that pallet of car batteries. This is an inductor. This particular inductor is the difficult part of the radio blast cannon. I'm going to get to that. Right here, we have our old friend, the spark gap in a cavity. In this particular case, the spark gap doesn't exist yet. I have the switch for this whole circuit is to yank this wire here. Pull it out. All of a sudden, I have a spark gap, and all that energy in this inductor is going to get pumped across that spark gap in one nice big pulse. The more quickly I can pull that wire out, the tighter my pulse is going to be, which means I'm going to deliver a lot more power. If I can get this all in 1 millisecond, that coil that I've designed is going to deliver a megawatt coming out that cavity right there. Now, it's only 1 kilojoule. A joule is a measure of energy. Only one kilojoule sitting in this inductor. Now, those of you who know what a joule is are going to say, only 1 kilojoule? What the hell is this guy talking about? What crack has he been smoking? Well, that's a really damn big inductor. So, once again, coming back to our high school physics textbooks, you can find out what inductance a inductor is going to have. You can sit here and wind your own inductor on a metal rod and get some inductance. You're going to know ahead of time if you've done the math. It's not very complex. You don't need any calculus for this thing. It's simple algebra. This particular inductor that I have is a 10 Henry inductor. A Henry is a measure of inductance. And that really tells me how strong the magnetic field is that I'm going to generate from this inductor. If I know the current going through there, and I know the inductance, I know the magnetic field. With that 10 Henry inductor, if I'm able to put 10 amps through the coil, I have enough magnetic energy there so that I'm storing a kilojoule. I want to emit that in a millisecond so I can get my 1 megawatt pulse. Now, we've got a problem here. Every circuit has parasitics. I don't care how well you do it. I don't care what ideal world you're in. There's going to be parasitics in there. So you're going to lose some of that energy. Not all of it is going to go downfield. The best you can really manage in any radio circuit is 50% efficiency. It sounds bad, but it's actually pretty good. That means half of the energy that you're trying to emit is actually going to go where you want to go. The rest of it's going to be heat, the rest of it's going to be maybe sound. It depends on how you've built the circuit. There's lots of sources of waste. So if I actually make my goal, I'm only going to send half a megawatt downrange. That's still pretty damn good. Commercial radio stations are only a couple megawatts, usually. And this thing, with 1 megawatt going downrange, is going to pretty much take out any computer you want to look at, if it's at the right range. If you were looking at this little laptop here with terrible shielding, I can probably have this maybe 100 yards downrange, and this thing's going to be fried by this radio blast cannon. On the other hand, if I look at a really well-shielded commercial machine, like the old Macintosh, I'm not talking about the Mac Classic, I'm talking about the original 1980s Macintosh. It's got great shielding on that thing. I probably have to be 10 feet away. Still, I can go through a concrete wall if I want to. No problem. Concrete's not a conductor. Maybe my desktop PC, 50 feet, 30 feet, who knows? Who made it? What kind of shell it has? I don't know. If it's plugged in, it's got that shell is grounded. That's going to be a lot closer to being a Faraday cage. It's going to be able to survive this energy a lot closer. But the important thing is I've got my energy. It's going downrange. It's going to hit my target. There's a lot of energy. This inductor, on the other hand, is a source of a lot of problems. Like I said, it's a 10 Henry inductor, and I want it to handle 10 amps. I don't care how small my parasitic is. In fact, in this particular coil, it's 6 ohms of resistance. It's DC resistance. 6 ohms is not a whole lot, but when you're talking about 10 amps going through that, that's a lot of energy that I'm losing. It's just wasted. It's heat. Also, 10 Henrys is going to take a lot of time for me to build up this magnetic field. With my pallet of Costco car batteries, I've calculated it's going to take 4 hours for me to charge up this magnetic field. So the best I can possibly do with this is firing it once every 4 hours. It's going to take longer than that because these batteries are going to be dead at the end of this. But that 4 hours with that little tiny parasitic there is going to throw all sorts of heat out. And this coil is thick. It's got a lot of layers of wire on it. That nice little 10 Henry inductor uses 3 kilometers of copper wire. Now, that's expensive. That was, why am I over there? That's the majority of this $400. I had to go out and buy a big spool of copper wire. I got a quantity discount, but it's still a lot of money, and it's heavy. And in spite of the fact it's being copper, I had to get an insulator on that wire. Otherwise, I don't have an inductor. I just have a big slug of metal. That insulation means I can't shed this heat, this waste heat, very well. So I have to find a way to do that. The method I came up with they're out of order. Oh well. The method I came up with is you can go down to Osh and get yourself some nice little copper tubes. Just 1/4 inch diameter. They don't have to be very big. While you're winding this inductor, and spending a couple weeks doing it, 3 kilometers, you can put these copper tubes in the coil. The whole point of this is to pump water through the inductor. Now, water's got a problem. It boils at 212 Fahrenheit. So I don't want it to get above 212 Fahrenheit. There's an easy way to avoid that. An automotive cooling system. Go down to your handy-dandy junkyard and get that Dodge Dart radiator for 50 bucks. Hook it up to those nice copper tubes that you have running through this inductor. Fill it up with water, and don't forget your 50% ethylene glycol. And use a water pump. Regular old automotive water pump. That Dodge Dart is nice. It had a separate water pump. It's not going to be open. I can just pull that thing off the car. Sure, it's heavy, but it's cheap. It's a junkyard. And all I have to do is hook up an electric motor to spin the water pump. Now I have a nice pressurized water cooling system on my 10 Henry coil. And I have a nice source of batteries that I can run that electric water pump on. So, back again to inductors and capacitors. I already talked about, we have these inductors. I put a current through there, I'm going to generate a magnetic field. Capacitors are very similar. I put a voltage across it, and I have an electric field. Inductors like to maintain the current going through them. They will suck the energy out of that magnetic field in order to do it. Capacitors like to maintain the voltage across them. They will suck energy out of that electric field in order to maintain the voltage. That's energy in those fields. Those electric field, that magnetic field, that's energy storage. And it's got an advantage. These inductors and capacitors, I can dump the energy out of those fields pretty quickly. I can't change the fields very quickly. As I mentioned before, this 4-hour charge time on the inductor for that RBOC. So it's slow to build up, but I can get the energy out quickly. That's not true of batteries. So I like storing energy in these things. Now that spark gap transmitter that we've been talking about needs currents. That's why I use an inductor in the radio blast cannon. On the other hand, if I had some kind of transmitter that wanted a voltage somehow, I'd use a capacitor. They're completely symmetric. If you want a voltage, use your capacitors. If you want a current, use your inductors. You can treat them identically. Just swap current and voltage. So, we've got that inductor trying to maintain a current through this spark gap. It's got a lot of energy to work with. When I yank that wire out of the cavity, the current immediately stops. The inductor doesn't like that. So it's going to start pulling energy out of the magnetic field to start the current going again. Eventually, it's going to succeed. And at that point, I have a lot of radio energy coming out of this thing. That spark is my transmitter. So, back to those parasitics. We know you always have to waste. Thermodynamics sucks. This inductor, it's got resistance, it's generating heat. We don't like that. We're going to get rid of it with cooling. We like that. There are other kinds of parasitics you can have. Capacitances. If I have two wires going next to each other, there's going to be capacitance between them. If I have a long wire, it's got its own inductance. When I run a current through that, it's going to try and maintain that current just on its own, because that current is generating a magnetic field around the inductor. Most of you should have done by now the take a nail, wrap a wire around it, and watch the iron filings line up. That's the magnetic field around this conductor. In most of these nice, cheap circuits, you don't care about the parasitic capacitance. You don't care about the parasitic inductance. That's good, because they're hard to control. Parasitic resistance is what's going to kill you. You're going to be dumping heat. Whichever three of those you have, you might even change the tuning, the resonance of your circuit. But the important thing is you're wasting energy. And that's where that 50% is going to disappear. In the RBOC, it's the resistance that's killing us. No, that's that cooling the inductor slide. So I've already talked about where to get a lot of parts. Radio Shack has a terrible selection, but it's convenient. It's got okay prices. So it's got my stamp of approval. Junkyards really have my stamp of approval. They charge you by weight. That's good. Electronics suppliers. Well, you can get pretty much anything you want there. That's nice, especially if you live in a big town. If you live in bumfuck Idaho, you don't have an electronic supplier nearby. So then you're stuck going to electronic suppliers mail order. Well, you guys saw the title slide of my presentation. We're going to piss off feds here. You don't want to do mail order. You get on lists. Feds like lists. We don't like lists. So that brings us to electronic surplus. They have a lot of the nice, fun toys that electronic suppliers have, but no lists. And a lot of their stuff at the electronic suppliers comes from the 50s, the 60s, when people like to deal with big inductors and big capacitors and fat wires. We like that. They're also cheap. Military surplus. Well, you can't get a whole lot of electronic components from military surplus, but that rundown Jeep probably has a radiator in it. Maybe it's got an ignition coil. Or we can look at the radios you can buy from military surplus. Really, if it gets down to it, I have a Yaesu FT50R. It's a little handheld radio. It's only 5 watts. But with the right target, that's a radio weapon. In fact, if I key up that Yaesu next to this laptop crashes. Like I said, this laptop is pretty lame. But any handheld is going to emit that radio energy. All you have to do is get the right range, get the right distance, or get the right frequency, I should say, and the right power. That's what's going to do it. I know somebody who will remain unnamed who modified a ham rig so that he could continue tuning it while he was keyed up. So he could push the transmit button and tune it. And he discovered that each of the big three cars, GM, Ford, and Chrysler, have fundamental resonant frequencies in the engine circuitry. We have a spark plug. When that's turned off, it's a capacitor. We have spark plug wires. Well, all cars these days use resistive wires. We have a resonant RC circuit there. If that engine is trying to fire, it's trying to run a particular type of signal, admittedly a real sloppy one, but a particular type of signal along that circuit. If I can impose a signal that'll resonate on that, I can turn the car off. It's not going to destroy the car, it's just going to disrupt it. The car has shut off. And he knows all three frequencies for the big three cars. Of course, there's all these people out there who've gone and changed their spark plugs and their spark plug wires. Maybe they now using solid core spark plug wires. A lot less resistance, well, that frequency is going to change. But it just shows to illustrate a standard, very slightly modified ham rig you can pick up in any store. You can use it as a radio weapon. It doesn't take a whole lot there. That's electronic suppliers. And I can keep on talking. But does anybody have any questions first? Anything that I've glossed over that I've lost you on?
Actual physical dimensions.
Actual physical dimensions for which? What? The resonant chambers. The Arbok uses a big industrial coffee can as its resonant chamber. You go down to Costco, Price Club, something like that, you get the nice industrial size 50-pound coffee can. Empty it out, drill a couple holes, you have a resonant chamber. It's cheap. It's sloppy. We like sloppy. In the hat in the back there. Solenoids. I made reference to the nail with the wire wrapped around it, lining up the nice iron filings. What I can do instead is suppose that nail isn't tightly attached to this wire. I've got a gap there, and I've got a spring on it. When I turn on this, start running current through that wire, I'll set up a particular magnetic field through that nail. If I try to suddenly change that current, we have a new path that the inductor can discharge its energy along. It can still try and restore the current, but there's another path. It's a parasitic path, but in this case we like that. It can move the nail. It's creating eddy currents inside the nail, blah, 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 advanced physics, but that's the solenoid. I can run a current, control this current along a metal rod, core, and pull that in and out. You can buy solenoids from Radio Shack. You can buy them from the surplus stores. Some of them are fast, some of them are slow. You have to be careful to choose the one you want, but they say on the package how fast they can operate. And you don't need a very big spark gap. You only need a little tiny gap to stop that current. So you don't have to move it very far. Sure, you can get a slow solenoid and still satisfy all the needs you want. Next. You right there? Electronic locks? A little bit. Electronic locks that are built by smart companies have a nasty feature. You destroy them or you disrupt them and they don't open. This isn't Hollywood. They don't just open up on you. Now, on the other hand, if you're talking about a lock on a fire door, fire regulations require those to open up. A good example is a lot of commercial buildings these days use magnetic locks on the doors, especially on glass doors. They'll have these big, huge panes of glass that are hinged, and up at the top corner you can see little metal plates. Behind those plates, what you can't see unless the door is open, is a magnet. It's an electromagnet. And if you can disrupt that magnetic field, you can make the door open up. Now, energy weapons really aren't the way to do that. Cow magnets are. Put a car magnet up against there, and a lot of times that magnetic lock will release. But we get back to the fire regulations. There's got to be a way, when the system fails, for it to open up. And it is going to open up. This isn't a lock that's going to stay locked when it fails. And if you can find a way, find a target to hit with your energy weapon, you can make it fail that way. You just have to find that target. Next. In the orange shirt. Repeat the part after sound generated. You asking me to elaborate on the heat and sound? Is that it?
How much heat will it throw off generally, like
Well, the sound is usually generated by capacitance, parasitic capacitors. And it really needs oscillating signals. This RBOC doesn't have much in the way of oscillating signals, so it doesn't generate a whole lot of sound. It can generate sound because if you put too much energy through a spark gap, then all of a sudden you have a plasma ball. And, well, that's fun. It's pretty, just a little expensive. So the biggest part is the heat coming off that coil. I mentioned we have half of our energy is disappearing there. It's 500 joules is being dissipated from that coil. And I have to keep that water running the whole time, circulating the whole time, or just like your automobile, when the water pump fails, my RBOC is going to overheat. The insulation in my inductor is going to melt down, and I've got a short. So yes, it's dangerous. It's a lot of heat. That's why I've got the coolant there. And this can come into play in anything that you do. In fact, it will come into play in anything you do. Some of you have used Ericsson telephones. When you talk on one of those for a long time, your ear gets hot. It's not because it's cooking your brain. It's waste heat from the electronics under the earpiece. And you're feeling that in your ear. It's uncomfortable. It's a lot of waste heat. Those telephones, those little tiny telephones, they dump out a lot of energy. They don't really have a good way to handle it, so it's uncomfortable. But a telephone, well, sometimes a cellular phone can be a weapon, like with this laptop. In the way back there.
Any reason why you hear this inductor instead of capacitors?
For which one? The radio blast cannon?
Yeah, radio blast.
Okay, the question is, why did I choose an inductor rather than a high voltage capacitor for the radio blast cannon? And the answer is, first, the current. This is a current-controlled device. The whole point is, I'm going to open up this spark gap and disrupt a current. Opening a spark gap isn't going to change any voltage across the device at all. It's going to change a current. So I want an energy storage device, a fast-acting energy storage device that's going to respond to this current. That change in current is the signal to my energy storage device, hey, dump your energy now. And inductors do that. High voltage capacitors don't do that. Yes?
Concentrated protection or defense, big metal plate, is that right?
Faraday cages are really nice things. They're cheap too. If some of you have heard of Van Eck monitoring, and a lot of you have heard of the government programs to protect against them. Basically, all those government programs boil down to building really nice Faraday cages. A Faraday cage is just a conductive shell. If I have a shell around something that's a good conductor, there is not going to be any electric or magnetic field in inside that shell that's imposed from the outside. Now, I can generate one inside there, but we're talking about an energy weapon. I'm going to be generating this field from the outside. So as long as I can have a good conductor in my shell, I'm going to have pretty good protection. And the better the conductor, the better protection. Copper is a good conductor. Steel isn't. Steel is a lot better than glass, but it's not as nice as copper. A lot of computer cases are made out of steel, so you don't have as good a protection. But you can buy copper shells. You can buy gold-plated gaskets to run around the edges to improve the contact between the pieces of your shell. You can also not piss off anybody who has the radio blast cannon. Right there in... Yeah. They'll blow what? Yep. What kind of voltage am I talking about to what? Well, these are just car batteries here. Each one is 12 volts. But I have a lot of parasitic resistance there. So in order to get 10 amps going through there, once again, we're back to the high school physics. E equals IR. The more resistance, the more voltage I have to match that same current. In this application, we're talking about 11 car batteries in series. So I've got 132 volts. Car batteries, some of you think car batteries are 14 volts. That's only true when they're charging off of a car. By their own, they're 12 volts. So I've got 11 of them, that's 132 volts. And the only reason I have the extra voltage there is for the water pump. Now, I don't know yet whether or not that's enough extra energy to the water pump and the coil. I still have to spec that part. That design part is done, but not the actual characterizing. Well, we get back to changing an inductance. I can make that charge time go down a lot. Oh, the question that was asked is there anything that can be done to reduce, I assume you're more interested in reducing the charge time. Is there anything that can be done to reduce the charge time on that inductor from 4 hours? The answer is yes. There's two things I can do. The complex, well, there's two, they're both complex. The more complex one is to alter the geometry of the inductor as I charge it. So if I start off with a small inductance, I can get up to a large current pretty quickly. Most of this charge time here is that the inductor is starting off with no magnetic field, and I'm trying to run 10 amps through it. The inductor is going to resist that by taking energy out of this incoming current and sticking it into the magnetic field. So what I do instead is I can start off with a lower inductance, and it's going to be able to build up the appropriate magnetic field much more quickly because it's less energy in that magnetic field. And then I can change the geometry of the inductor so that as it charges, I build more inductance into the system. And that's one way I can speed up the charge time. The other time is I can vary the current. Instead of starting off trying to run 10 amps through it, which is what I do right now, I can start off trying to shove 100 amps down its throat. And it's going to build up the magnetic field a lot more quickly. And I can't do that when I get near the end of the charge time. I'm going to have to reduce that current, or I've got the wrong magnetic field for what I'm trying to do, and my batteries aren't going to survive. Question there?
Can you reduce the charge times and staging the inductors? Instead of changing the size of the inductor, having moving parts, when you actually
the question was, instead of having the moving parts to change the inductance, can I have multiple inductors, multiple smaller inductors to work with? And the answer is yes, but the energy storage in inductors in the magnetic field. So in order to be able to dump my full kilojoule when I want to do it, I've got to make sure I've got a single magnetic field. What I'm going to be switching here in that circuit that you proposed is the geometry of the magnetic field. I'm starting off with 3 separate magnetic fields, and I want to bring those together so that I have a single magnetic field running through these coils. And that way I can have, effectively, one larger inductor. And that's a hard thing to do. Yes, I can do it, but it's a lot easier to do that electronically rather than magnetically, or rather than physically. So, I mean, yeah, it's a possible thing. You're getting into raising the cost again. So, we're trying to keep this inexpensive. Right there by the projector? Yeah, you. What's that?
Have you actually fired this thing?
I have fired a weaker prototype. I have fired that. I have not fired the actual radio blast cannon that I've described here. On the edge there, you had your hand up for a while.
I was reading some reports, and I guess it was a DoD test of energy weapons using large magnetrons over water, and they had some pretty impressive results. What would stop a home tinker from using like surplus microwave parts and have a cluster of magnetrons? Do you think it would be feasible to do it that way, similar to when the military was testing?
Well, the big thing, okay, the question was, he's read about the military using clusters of large magnetrons that are water-cooled to produce a lot of radio output. And how come the home experimenter can't really use that tactic? Well, there's a couple of reasons. First, the magnetrons are very inefficient devices. Now, a magnetron, for those of you who don't know, this is the device inside a microwave oven that generates the energy that cooks your food. Now, it's radio energy, just like everything else we've been talking about today, but it's at a very tight frequency. And the magnetron works just like the spark gap in a cavity that I've talked about before. But the magnetrons themselves, that device isn't all that efficient, and it's very expensive. I can go out, the cheapest way for me to buy a magnetron right now is to buy a complete microwave oven and just strip the magnetron out. I can get a microwave oven for like $75.
Well, you can buy one, like, go garage sailing or, go to a flea market or something. You can pick up like 10 microwaves for $5 each every weekend for a month and have enough to like build a pretty sizable weapon.
Yeah, that's true. That's true. That would work real well. Garage sales. I should add garage sales to my suppliers list. But then we come to the other problem with magnetrons. Magnetrons are very tightly tuned. I can't produce a nice sloppy signal coming out of a magnetron. So if I happen to be targeting a device that's very well shielded at that frequency, I'm going to do nothing to it. Now, on the other hand, if my target is a raw potato, it's going to cook real fast. Because these microwave magnetrons are tuned to the frequency, the resonant frequency of a water molecule. Now, here we are in Las Vegas. It's been real humid the whole time we've been here. There's a lot of water molecules in the air. That magnetron-based device isn't going to do anything but heat up the air. Yeah, some of the energy is going to get through to the target, but not as much as we'd like.
The reason I bring it up is the military tested, like, they had impressive results, like detonating landmines from 3 miles, like all kinds of like crazy stuff. What kind of power would you go working with that? Have you heard of the test?
I haven't heard of the test. I'm just assuming that everything you've told me is accurate. And I mean, yes, it's a credible claim. Yeah, the military could do that. But once again, back to slide number 4, military has oodles of money to play with. So they can do it. Right there? Oh yeah. Oh yeah. 10 amps will kill you very easily. It only takes a dozen milliamps to stop a heart. That's it. But you got to get it to the heart. Skin is a relatively good insulator. Blood is not. Blood is a great conductor. So that 10 amps, if I'm going to try and run 10 amps through my body, yeah, it's going to mess me up real bad. It's probably going to kill me. Come down to an amp, that's still going to kill me. And it's going to be painful to boot. But if I can drop this whole circuit down to maybe, 200 milliamps, 300 milliamps, that's fine. And that brings us to the cell phone jammer. That's where that operates. In the back, the striped tie-dye.
How do you think you might have been victim?
If I think what?
Like, what exactly does it do to your computer? Like, your computer works for 1 minute, you walk down the street, you plug it back in. How can you tell that
It sounds like you're asking, how do you tell if a computer has been damaged while it's been turned off? Is that true?
Radio blast.
Well, the radio blast cannon, my intended target is computers that are turned on, because they have more sparks. But if a computer's turned off, I can still damage it. And yes, unless something critical happens, I mean really critical, letting a lot of magic smoke out, you aren't going to know it till you try and turn the computer on. And it's a lot easier to damage a computer that's turned on because we have CMOS circuits use transistors, or use CMOS transistors, which are controlled by a gate. It's a capacitor there, and these circuits, these transistors are going to turn on and off, changing their conductance. If the computer's turned off, then those transistors aren't switching for me. So I can get to more places in the computer while the computer's turned on. Right there? Yeah.
Have you actually done any experiments to see if the dimensions of your cavity change how effective the device is? Because no matter what, you're going to have impulse, which is opposed to a broad range of frequencies. So if you're trying to for a certain frequency, the shape or size of that dimensions of the cavity are not going to have as much of an effect as if it's a resonant continuous device. You're using a spark gap.
Right. Okay, the question was, have I done any experiments as to the effect that changing the geometry of my resonant chamber would have on the effectiveness of my device? And the corollary assertion he made is that my spark gap is spitting out energy at a lot of frequencies, which is absolutely true, and this resonant cavity is going to accentuate some frequency, so I'm losing a lot of the energy that is generated by, that is being produced by my spark gap. It's not going to go downfield. And it's absolutely true. Some of my energy is going to be lost that way. But we get into plasma physics here. Some of that energy is going to be reabsorbed by the spark, and it's going to have a chance to be re-emitted again. So I don't lose as much energy as you would expect. Plus, I have a nice sloppy coffee can, so I'm getting a lot of energy out at different frequencies, which is precisely what I want. I don't want a tightly tuned cannon. With the cell phone jammer, I did a lot of experiments about changing the geometry. I changed the position and the size of that pickup coil that I had around the spark gap. I played around with grounding the shell of the resonant cavity or leaving it open, a lot of different things about that. And yes, that can have a very large effect. But once again, it's tuned to a specific application. As long as I know what my target is while I'm designing the weapon, yes, I can tune the weapon to that target and produce a much better effect. But the radio blast cannon, I'm trying to hit a wide variety. So I really can't tune that ahead of time. I want it to be as sloppy as possible. Right there, behind the red hair.
What are the laws concerning the creation and using components in these places?
Thank you for asking that question. I wish you were a plant. The question was, what are the laws that affect energy weapons of this kind? And that brings us into the whole political issue of the home experimenter. We all know Well, certainly all the Americans here remember way back when a certain congressman's cell phone call was recorded and broadcast and rebroadcast and rebroadcast, and he didn't like that. So we have some laws on the books now. Not only is it illegal to listen to cell phones, it's also illegal to produce a device which is capable of disrupting cell phone communications. Yeah, that's pretty screwed up. You can't even produce the device. Now, against an intelligent defendant, it's hard to get a conviction, but you have to have a good lawyer, all that stuff, get your advice, blah, 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 blah. And of course, we have FCC licensing things. The FCC license frequency ranges, and if you transmit above a certain power within those bands, then you can get in trouble from the FCC. Now, it tends to just be your equipment gets taken, you get a fine, things like of that nature, but it still sucks. I mean, who wants to deal with that kind of stuff? Yeah, you really can't direction find an impulse, but on the other hand, if you're stupid enough to come to DefCon and speak about all these radio weapons you've been building, they don't need to direction find the impulse. So, and there's other political issues involved here as well. All of this information I've presented is from high school physics textbooks. Now, if you look at the popular press, if there's any popular press present, and they actually choose to discuss this seminar, they're going to talk about these evil hackers who are using all this arcane knowledge. It's not arcane at all. This is basic high school elementary physics. They can get rid of it as soon as physics is no longer taught in high school. And I sure hope that's not going to happen. People will try to limit things like that. The whole keeping track of who checks out books from libraries, of certain sensitive subjects, things like that. And there's a lot that the government can do to make your life miserable without worrying about the law. Yes. Well, let's see if there's somebody who hasn't asked a question yet. Okay, go ahead. It depends. If you have a really good Faraday cage, it doesn't need to be grounded. It's a conductor. That's all that matters. So I can get into the... Now, for Faraday cages, yeah, we have to talk about calculus, unfortunately. Talking about integrating Maxwell's equations across the surface and the volume of the Faraday cage, and that's evil. You don't really want to be dealing with that. If you've got a nasty, poor shield, then a lot of times it does indeed help to ground it. Because you've got a Faraday cage, which is this big metal object. I hit it with a lot of radio energy. Some of that energy is going to couple into the shield, into the cage. If that can't be dissipated, then some of it is going to be re-radiated inside the cage. And the big deal about that is the sheet resistance of the cage. Gold has a really low sheet resistance. Steel has a relatively high sheet resistance. Aluminum has a huge sheet resistance. And the higher that sheet resistance, the deeper those charges. When I impose energy onto the Faraday cage, free electrons in that metal are going to start moving around. And the higher the resistance, the deeper those free electrons are going to move. If they get to the inside surface, then I have radiation inside my Faraday cage. And the higher the resistance, the thinner the cage, the more energy I impose on the cage, the better the chances that some of those charges are going to get to the inner surface where they can re-radiate. If I ground the cage, then I can slough a lot of this energy off down through the ground into the planet, and the planet's a great conductor. It's wonderful. I mean, yeah, dirt kind of sucks as a conductor, but it's big, it's wide. So I can shove a whole lot of energy down there, and that protects those electrons so they don't have to get deep into the cage. They aren't bouncing against each other as horribly. Anybody next? In the back there. What was that? Yes. Radio weapons can generate biological effects on human beings. Human beings are electronic devices. We have a nervous system. We have a blood system. That's a really good conductor, the blood. And each neuron is controlled by the voltage between the surrounding fluid and the inner fluids inside that neuron. If I can change that, I can change the action of that neuron. Now, of course, with this kind of stuff that I'm talking about here, you don't have any pinpoint control here. You can't say, that neuron fire now. But you can disrupt a lot. There is an effect that most of you should have experienced. I'd be really amazed if any of you haven't. It's called a phosphine image. If you close your eyes and press on your eyelids, you see these shapes inside your eye, and they're totally fake. They result purely because the change in phosphor permeability of the neurons in your optical nerve bundle, right back here. You press on your eyes, you're increasing the pressure, you're changing that. I can change it as well with a whole lot of radio energy. So if I hit you with a bunch of radio energy, I've changed the voltage across those neurons. The phosphor conductivity is going to change. You're going to see phosphine images. I don't know how much it takes. I don't know what frequency it's going to really want. And I really don't want to be the target of something like that. So the answer is yes, the theory is there to say that you can produce a whole lot of different varied biological effects with radio weapons. As to whether or not you'll ever find somebody who will admit to experimenting on it, I'd say no. Right there?
I've heard there's actually been some research done. The easiest way to simulate is to affect the human is produce something like ultrasonic
You ready?
mess with people's inner ears, essentially mess with your inner ears, and they can follow it.
Well, it's a lot of it wasn't really a question. The statement was that he's heard of experiments with, were those radio weapons or sonic weapons?
It's an ultrasonic weapon.
Ultrasonic, yeah, I can believe that.
Yeah, it doesn't.
Yeah, it was about energy weapons that can mess with your inner ear. Specifically, he was talking about ultrasonic weapons, and it would make you lose your balance, maybe fall over, things like that. And yes, absolutely, it's completely credible. The whole point of the ear is to couple sonic energy. That's why it's there. And it's really good at doing it. So if I shove energy, sonic energy, down your ear canal, I can make all sorts of different things happen. And your inner ear is right there. It's got some bones around it. Bone is also a good conductor of sound. I can do all sorts of stuff with, well, I'm saying I in the hypothetical generic sense here. Do all sorts of things with those kinds of ultrasonic weapons. And it's just like the butt guster. All we're doing here is we're trying to impose a sound which is resonant with your gastrointestinal tract. And it works. It's not too hard. It's real close to 16 hertz, but I didn't say that. Okay, so I can only really take one more question before we have to start going to the next seminar. Right there.
Do you know of any studies or research that have been done to characterize the reflectivity of average as far as radio energy? Like, what do they look like if you were to throw a square falls at them?
Okay, you're asking about the radio reflectivity of the average human body.
Correct.
Okay. Well.
I mean, they know lots of things, something, but here's what can happen.
Right. There has been a little bit that I'm aware of, but mostly it's at exotic frequencies. This kind of stuff that I'm talking about is pretty low frequency. It's regular old radio stuff. We're talking about hundreds of megahertz, things like that. But the few little exotic experiments I've heard of about actually trying to get a radar cross-section on a human body are pretty up there. We're almost talking daylight here. So it's good. You can get a really great radar cross-section on the human body with ultraviolet light, or infrared light, or a purple light bulb, or this laser pointer. It works real well. But down here at the really easy to manipulate radio frequencies, no. The biggest problem with it is that down at the radio frequencies, human beings are tiny. If an object is smaller than half a wavelength of the energy, you get really terrible coupling. And okay, if I'm going to shove a signal at you that's 40 meters long, you aren't going to couple much. So I have to get up to some size where you are large compared to that signal. And that's because you're a bad conductor. So, that's it.